Hello fans, it's Abjoin Babatunde Kukola again for this channel, Nubia Preset Designer. How are you guys doing? Hope you're enjoying our videos. If you are, I will implore you to like and subscribe to our channel, because on this channel we create video that teaches the rudiment of chemical process design. We discuss topics and methods to use process simulation software like Aspen ICs, Aspen Plus, and ChemCAD, Unison, etc. And we also work on process drawing, process modeling, plant layout, and on chemical engineering analysis, thermodynamics topic. And so, if you haven't subscribed, please do so that these videos can get to more audience around the world. So today we are continuing from where we stopped on the course series that we are doing on shortcut binary distillation with Microsoft Excel and VBA. We stopped in the last video on the estimation of the stage's temperature. So we estimate the stage temperature based on the composition of the stages. We are following the theory that the temperature, the vapor that is leaving the stage is at dew point, while the liquid that is leaving the stage, equilibrium stage, distillation stage, is at bubbling point. So today we are going to continue in calculating the condenser duty and the boiler duty. But before I do that, I want to take note of one mistake that I made in the previous video in the calculation of the feed quality. Following my presentation in the previous video, this is the equation that I presented that I'm using to calculate the feed quality, which is the enthalpy of the feed minus enthalpy of the feed at bubbling point divided by enthalpy of the feed at dew point minus enthalpy of the feed at bubbling points. Although H is a specific enthalpy, not really enthalpy, you understand? So, but the difference between enthalpy of specific enthalpy of the feed at dew point minus specific enthalpy of the feed at bubbling point is the rate of vaporization of the feed. You understand? So, but the correct formula is actually enthalpy of the feed at dew point minus enthalpy of the feed divided by enthalpy of the feed at dew point minus enthalpy of the feed at bubbling point. You understand? So the meaning of the feed quality is to calculate the amount of heat that is required to vaporize the feed. That is the quantity of the quality of the feed. You understand? So the amount of heat. So the more heat is needed to vaporize the feed, the more the quality of the feed. You understand? So so this is not the correct formula. Although from the equation, because I copied it from the previous model that I've done. So the equation is actually correct, because D44 is the enthalpy of feed at dew point, while D45 is the enthalpy of the feed at bubbling point, while D43 is the enthalpy of the feed. So the equation is correct. So, and because I was using this if statement before, because I thought the quality cannot be greater than 1. It should be in the range of 0 and 1. So I'm going to remove the feed quality, because the quality can be greater than 1. So I'm just going to copy the equation, the original equation, instead of using the if statement. So because the quality can be greater than 1 if the temperature of the feed is lower than the bubbling point temperature of the feed, and the quality will be less than 0 if the temperature is greater than the dew point temperature of the feed. So that's the case. So if the quality is okay, if the quality is greater than 1, when you put the feed into the distillation column in the feed stage, some of the vapor that is coming, because the feed is having more cold energy, you understand? So some of the vapor that is coming from the stripping section will condense into liquids to that stripping section again, you understand? So it's going to take some of the vapor, and all the feed will also go to the liquid in the stripping section, you understand? While if the quality is less than 0, that is the feed is superlated vapor, so some of the liquid that is coming from the rectifying section will vaporize back to the rectifying section, and all the feed will also join the vapor that is going to the rectifying section. So that's the implication of that. So once I have done that, so then now I'm going to, so if I change the temperature to something like 50 degrees Celsius, which is less than bubbling point temperature, you can see the enthalpy of the feed is now very low, and the quality will be greater than 1. When you copy the value here, to be greater than 1, you understand? And it will affect the vapor flow rate and the liquid flow rate in the stages, you understand? So I will clear this so that we can do other things. So we go to the enthalpy calculation. So for the heat of condenser, I'm using okay this is the equation that I'm using for the heat of condenser. So I'm doing energy balance around the condenser. So in the condenser, we have one stream that is coming in, which is the vapor from the top stage, while two stream is coming out of the condenser, because it's a total condenser. So we have distillate that is coming out and the reflux L, you understand? So I'm doing energy balance. So the H, like I said, H is the specific enthalpy of the stream, you understand? And I'm using the CP calculation to calculate the H value, you understand? So the total energy that is coming into the condenser must be equal to the total energy that is leaving the condenser. So V will be the flow of the vapor that is coming from the top stage, and HV is the specific enthalpy, specific molar enthalpy of the vapor stream that is coming from the third stage. And this is the temperature of the third stage. Any stream that is coming from any stage should have the same property of that stage. That is the notation. Then plus Q condenser, this is it in terms of enthalpy, that is in terms of material, and this is now the duty that is applied to the condenser. Then you have the heat that is coming out with the material, which is the distillate and the reflux, you understand? And Tc is the temperature of the condenser, you understand? And Hd is the specific molar enthalpy of the distillate, and L is the reflux, and HL is the specific molar enthalpy of the reflux. Then since the V is for material balance, calculation, V is going to be equal to D plus L, you understand? So we can easily summarize this equation into this form. And the equation that I'm using to calculate it, I've already copied it over here. So, and something you should take note in this equation is, because I'm not using it like that form, because this one is using the L4, which is the heat of vaporization. So it's because we we have already established that the T1 is the dew point temperature of this composition. Like V and D should have the same composition because it's a total condenser, you understand. And T1 is the dew point temperature and Tc is the bubbling point temperature, you understand. So the difference between the enthalpy should be the heat of vaporization of the composition, you understand. That's why I'm using it directly, so just to shorten the formulas, you understand. So then you have the 60 times 60 just to convert the units from from hours to seconds, you understand, because I'm writing it in kilowatts, you understand, and the flow is in kilomole per hour, you understand. So I just have to convert it to seconds. So we have that. So I'll do the for the second one. For the second for the Q Ebola, I took the overall material balance for the whole column. So if it for the second Ebola, I took the overall energy balance for the whole column. So for the flow in, we have the feed, then a specific molar enthalpy of the feed and temperature of the feed, then the heat that is applied to the column, which is the QC and the QR, you understand. And because I use negative in front of this heat of vaporization because you are condensing, you understand, so it has to be negative. So we have the QC and QR, then the distillate, then the HG, then the TC, then W distillate, then flow that is coming out of the column, and this is the distillate that is coming out of the column, and the bottom that is coming out of the column. So the distillate is coming out temperature of the condenser, while the bottom is coming out temperature of the boiler. So this equation is rearranged into this form to get the Q boiler, you understand. So that's all the thing. So the equation is here. So this is the equation over here. So we have this for enthalpy of heat required for reboiling. So we have the flow of the this is flow of distillate. This is the temperature minus temperature of the reference. If you click on it, this is for the temperature of the distillate, R15, you understand, and this temperature for the reference temperature, C5, you understand. Then I did the same for the bottoms too, is the O24, and temperature of the bottom of the reboiler, you understand, and reference temperature, then multiply it with the minus the feed, you understand, temperature of the feed, you understand, and enthalpy of the feed, because enthalpy of the feed have already been calculated over here, you understand. So then change it to per seconds and subtract the Q condenser from the equation. So that's it. So we have the energy of the condenser and the energy of the reboiler done. So the next thing to do after that is the modeling of the equilibrium curve of the distillation column. And to do the equilibrium curve, we are making use of the term that we call relative volatility, and relative volatility is the ratio of the saturated vapor pressure of the light component divided by the heavy component, and it's to relate the equilibrium composition of the light component, you understand, with respect to the heavy component. So at average temperature of the column, so I think the first thing that we should get there is the temperature, average temperature. Then we get the relative volatility. Then this is the, like I said, the relative volatility is used to relate the equilibrium composition of the light components. You understand? Like this is the vapor phase mole fraction and the liquid phase mole fraction of the light component for the stages. You understand? So and we need to get the T average first. Then we get the relative volatility, and we assume it is constant. Like, you understand, so that in with average temperature, because relative volatility will be changing with the temperature of the stage. So each stage is supposed to have different relative volatility, or even each section of the stage. Like this, if you want to model the system rigorously, you understand. So but we are making it as simple as possible. So that's why we just assume average temperature for the whole column. And so my formula for the average temperature is basically the mean of the first top state temperature and the last state temperature. So because the temperature will be interpolated on for the number of stages that we have, you understand. So but since we are not calculating temperature for the other stage, so we can just use this value. And the if statement is there, assuming you want to put your own average temperature, you override the one that you have is calculating. You can easily override the average temperature and it will work. So this is the value that the formula returns. So we have 91.64 degrees Celsius. So it is top state temperature. You can see top state temperature plus last state temperature divided by 2. Yes, so then the formula for the relative volatility, like I said, P sat. So but I have to write the equation like the one that we have been doing. So we write the equation out, but it's going to be based on the average temperature, because it's in logarithm. Then you find the exponential of both sides. You understand? So and we have the parameters for the Antoine equation, and the temperature is, you can see, 018 for all the Antoine equation parameters, the 018. So it will calculate the relative volatility, which is equal to 2.59. So relative volatility should be greater than 1, because you expect the saturated vapor failure of the light component to be greater than the saturated vapor failure of the airy component, unless you want to do it other way around. So once you are done with the relative volatility, we need to plot this, because this thing is for the equilibrium curve. You understand? Like I said, it's to equilibrium composition of the stages. You understand? So we write this equation out. So I've already written the formula for the, so this is the formula here. Y this is the relative volatility. R10 is relative volatility. Once I copy it in, you will see. So we have this is where I want to plot my equilibrium data. So I'm going to put the value here. So once you have it here, so it's going to be based on the value of x. You understand? Like we have the C62 is the x value. You understand? I can say I put a dollar sign in front of the R so that to make the relative volatility constant for all. I'm going to copy this formula for all these entries here. You understand? So I don't want to be changing the formula. I don't want the formula to be changing for the relative volatility value. I want the cell to be fixed. You understand? So I'm just going to click on the copy box here to copy it down. So because I'm making a lot of data, so that the relative equilibrium curve will be accurate. You understand? So okay, that's plot the equilibrium curve. So I'm going to do something like this just to copy the formula. I don't know why. To copy the format of the cell. Okay, that's copied so that it's not need again. Okay, so the next thing is to plot this thing, but I've already done the plot. Just disable the plot. So I'm going to be plotting the data again. So, and you can see the equilibrium curve here. So you plot the data now. You can see it's now on the plot. So to the data is already selected for the curve. If you just click on edit there, you see it. You can see. So the data is already selected already, and the y, which is just what I just calculate now. So then so that was the data. So and you have the plot for the first data. So I'm going to plot for the others too. That it's just automatic. It's just the same process that I did for the first plot. That's what I'm going to do for the others too. So these two, I'm going to do the equilibrium. So that's the equilibrium plots on of the stage. So the next thing to do is okay, because we are using McCabe-Thiele method, so we have to discuss some important line and equation. We have the equilibrium curve that we have already done, and the next thing is rectifying operating line and stripping operating line and the queue line. The rectifying operating line it depends on the reflux ratio of the stages you understand. Like the operation because the operation of the colon depend on the amount of reflux that you are using, you understand. The number of stages that is needed, you understand, for particular separation depend on the amount of reflux, you understand. So if you are refluxing a lot, if your reflux ratio is high, that is your reflux is also high, you understand, R is going to be L over D, you understand. So that means you are going to be needing lower amount of stage for the separation. But if your reflux is low, you are going to be needing high numbers of stage for the separation. So, and the second one is the stripping, that is the analogous one for the stripping section, and it depends on the boil-up ratio. And you can see from the equation of the reflux, which is the y, that is vapor phase move fraction for the next stage that is coming to the stage at the bottom, you understand, and this is the mole fraction, liquid mole fraction that is going to the bottom stage. So this equation relates the mole fraction of the vapor that is coming to that stage with respect to the mole fraction of liquid in that stage. You understand why for the stripping it relates the mole fraction of vapor that is leaving this stage, you understand, with respect to the mole fraction of liquid that is coming from stage on the top, you understand, and it has the S of distillate, or the mole fraction of the light component in the distillate and mole fraction of the light component in the bottoms for the stripping operating line. Why the Q line is depending on the kind of feed that you are putting, you understand. So because your feed also affects the quality of your feed, also affects the column, you understand. So this is it depends on the X and Y, you understand. I'll be showing the effects as we are plotting, you understand, and it relates the X and Y or on the plot, you understand, and we have the mole fraction of the light component in the feed. So let's start with the Q line first. So for the Q line, this is the first step that we are going to be plotting the Q line, and it's going to be calculated from the equilibrium curve. So I'm using just simple mathematical domains, just like your equating the value, because we are having X, we are going to plotting the same two lines on a plot, you understand. Instead of using a ruler to trace the point of interception, you can just write it in equation form, because you cannot using electronic screen, you understand. So you have to use equation to calculate the points. Just plot the diagram just for visualization sake. So we have two equations, the equilibrium curve equation and the Q line equation. So we are going to look for the X value that corresponds to the intersection points of these two lines, You understand? This is the equilibrium curve line, while this is the q line. You understand? From the x is, this is what we call the x is equal to y line, that is just the line that breaks the graph into two. You understand? So this is the q line. You understand? So I will look for the points, that the intersection points through this equation. So for this points, I just rearrange this equation, that is because it's just equation, I solve this equation. So by subtracting the term here from the term here, I got a quadratic expression. We know the relative volatility and the q. You understand? So this is the solution from the equation here. So from this step to this step. So since it is a quadratic expression, it can be expressed in this form, and the x value can be gotten through the general formula. You understand? So we have minus b plus or minus square root of b squared minus 4ac. So our b is q minus or mole fraction of light component in the feed, bracket alpha minus 1, then minus alpha q minus 1. You understand? That's our b. Then our c is minus mole fraction xf, and this is our a. You understand? So, and to illustrate this in Microsoft Excel, this is the section that I'm doing the general formula calculation, and you can see for my b is this value that I've just explained here, q alpha minus 1, and this is my a is this value that I just explained here, q alpha minus 1, and this is my b. F18 is q. You can see F18 is q. If you move up, I don't want to spend a lot of time. You can see F18 is q. Then we have this other value. F16 is mole fraction or xf, so which corresponds to this minus xf. Then R10 is the relative volatility minus 1, then R10 SF minus 1, which is the same thing. R10 Q minus 1, sorry, F18 is Q minus 1. You understand? So that's the B time. Then the C is just minus S of, that is mole fraction of light component in the feed. This is this term F18. So from there you have your ABC. Then you look for the determinant is equal to b squared minus 4ac. Then if the determinant is, this is just like if statement to tell you if the determinant is greater than 1. You can't, if you are finding the square root of a negative number, it will return error in Microsoft Excel. You understand? There is no complex number configuration in the code. You understand? So we have the intercept here. So if this thing is, if the determinant is positive, you understand, then it will calculate it will calculate the general formula here. You understand? So if this time is true, it will use this formula to calculate it. If it is 0, square root of 0 is undefined. You understand? So it's going to just rearrange the formula. You understand? Use the term to be 0. You understand? And just it will substitute this term to be 0. You understand? It's going to be minus b over 2a. You understand? So we have that. So we have this this y-intercept too. You understand? So the y-intercept is just gotten by just plugging the value of x. So since we have already known the x value, you understand, so we can plug in the x value in any of the two equations, then you get your y. So your y should be the same point too. You understand? It's on the same planar surface of the graph. You understand? So that's your x-intercept. So from here we can get the point that we need to plot the q line. You understand? So you can see from this point, this is my data that I'm using for my q line. It is starting from the feed point. Okay, let me try and enable the plots in my q line. Okay, so I'm going to be using the plots here. So like I have done for the equilibrium curve, I have already done for the Q line to just explanation. So for my Q line, you can see just plotting the data. So the first point is from the x self, you understand, because the x and y, the x is going to be y line should have the same mole fraction of the of the in the vapor phase and the liquid phase, that is the x and y, you understand. So it will help us to locate the point that is the Q line is going to start from, you understand. So to make it to be to be neat, that's why I did it. I started it from the bottom here so that it will be explanatory. So we have the mole fraction starting point to be 0.45, that is from the SF, that is the mole fraction in the feed. Then the y is going to be from the 0, so that the point will start from the bottom of the plot, you understand, from x axis. Then the points in the x and s is going to be equal to y, that is the 45-degree line, you understand. So we have the 0.4, each is equal to this time, you understand, just like a plotting values, you understand. Then the last point, which is gotten from this point, you understand, gotten from this point. So that's the meaning of this plot. So then it will just plot it over here. So I'll do for the second one too, so that we can see the plot in the second, because we are going to be needing Q line in the minimum reflux ratio too. Okay, done. So this is the y is going to be equal to x, or x is going to be equal to y line, that is the 45-degree line, just is at 0.00, then at 0.11, just like 45-degree, like bisecting line, you understand. So we have the so then after that, the next thing is calculation of the minimum reflux ratio. So for the minimum reflux ratio, it's just the difference is like to plot minimum reflux ratio in McCabe-Thiele method. The line, the operation line, is the line that starts from the mole fraction of the distillate, that is the distillate mole fraction, light component mole fraction in the distillate, and joins the point where the Q line intercepts with the equilibrium curve, you understand. So that's the minimum, that the separate that's the minimum reflux ratio, because as you are increasing the reflux ratio of the column, the slope of this line is going to be increasing. So you expect the stage to be having more separation, you understand. So if you are reducing the reflux ratio, the slope will be reducing, you understand. So that means the line we want to join, we want to overlap the equilibrium curve, you understand. So the minimum that to calculate the minimum, you have to draw the line from this Q line intersection, you understand, to get the minimum reflux ratio. So for the to do this in equation, you understand, not graphical method. So I am following the formula. So this is the operating line for the, and I told you we are going to do operating line for the stages, you understand. So this is the operating line for the minimum, like it's just like the rectifying operating line, but now the reflux ratio will be very low, you understand. So if you know the y-intercept to the y-axis, that is the y-axis intercept, you understand, we can know the minimum reflux ratio by just using this equation of a straight line, you understand. So this is the slope of the line, this is the y-axis intercept, that is when x is going to be 0, what is value of y, you understand. So when you rearrange this equation, you can get your r mean, you understand. So if y-intercept is going to be x0 over r mean plus 1, then r mean will be equal to sd divided by y-intercept minus 1 to get it. So what we should be looking for is the y-axis intercept of this line, you understand. So to do this, you know, since we know the we don't know the r mean, you understand, and we know this, and this line must pass through the intersection of the Q line and the equilibrium curve, you understand. So I just do some interpolation of the or proportional calculation for the line's slope, you understand. So because it's a straight line, you understand, that is the difference between this point, you understand, that is is starting from the mole fraction, from the light component mole fraction in the distillate composition, you understand. So the difference between the value, you understand, and the x, you understand, because we're having, this is from the 40-degree, that is the bisection line of the graph, you understand. So the value of x is the same thing as the value of y here, you understand. So then that will be the same thing for the overall, you understand, which is y minus xd, and is 0 because the x value for this point is 0, you understand. 0 minus xd, you understand. So this one is from the x value at this point, you understand, and this is the sd, you understand, because sd is actually 0.8, and also yd is also 0.8, you understand. So I don't want to confuse you guys, that's why I didn't put yd, you understand. So then we just solve for this equation. Since we know the y star and the s star, you understand, so we just solve for this equation. We're able to get y is going to be equal to sd minus sd, y star minus sd, s star minus sd, and this is the equation that we have for this Albumin plot here. So for the Albumin plot, I did the same thing that I did for this Q line plot, you understand, starting from the mole fraction of distillate, the specified mole fraction of distillate, of light component mole fraction in distillate, then the starting point, because I want I would like to plot this so that I can show it to you guys. So I did minimum reflux ratio here. So okay, that's it. So you can see starting from this point 0 and xd, you understand, 0.0.881, 10.0 here, then the 45-degree line, you understand. So we have the 0.8 and 0.8, you understand. So then the last point is going to be this from 0, you understand. This one is just like, if this equation is true, it's just like so that if it's not true, you understand, it won't calculate error, it won't transfer error to the other section, you understand, because the value here will be wrong if this determinant is not greater than 0, you understand. So, and we have the value here, you understand. So if it's also true, then this is the equation, you understand, that is sd is 0.08 in the cell reference, you understand. So, and you have the other j, which is this value, these two intercept value here, right here, you understand, j63, j62, you understand. So then if it is not true, you just use g65, g85, which is this value 0.8, that is the sd mole fraction, you understand. You understand. So that's it. So then it will just plot the calculated value on the graph so that we can see what is going on, you understand. So that's that on calculation of the minimum reflux ratio and the q line intercept, and plotting the value in Microsoft Excel. So thank you for watching. So I'll be ending this video today so that's not to make this video long. Yes, sir. So in the next video we are going to finish this course series. We are going to be discussing more on calculation of the operating line of the stages, calculation of the stage steps, yes, and number of stages that is needed for the separation at the particular operating condition of the colon. You understand, the operating condition actually depends on the reflux ratio, the boil-up ratio that you are using, you understand, and the incorporating the stage efficiency in the calculation, because stage efficiency we affect the mixing of the stream that is coming into the stage. If the mixing is not efficient, is not 100% efficient, You understand that the stream that is leaving the stage will not be in equilibrium. You understand? So the stage will not be efficient, and you might need more number of stages. You understand, to get to the separation that you want. So stay tuned and continue to watch our video. So thank you for watching this video.